numbering, it doesn't have to start at 0, 0. All right? It doesn't have to. But most of ours were convenient to start at 0, 0. That's fine. Numbering should be nice and convenient. Something easy to read. You know, 1, 2, 3, 4, 5, 6. You know, 2, 4, 6, 8. Something like that. Tens, fives maybe. You know, but usually it's got to be something really easy. So not threes, not sevens, right? Yeah, not 3.5. I don't even know what the next one comes after that. 7, and then what?
10.5.
Then what?
14.
What?
17.5.
Okay, y'all are too smart for me. But that makes it too hard to read. Now you can actually figure out what the next ones are, but if I ask you, like for instance, if you do that, if you do 3.5, 7, 10.5, and so forth,
He forgot.
the problem 14,
The values in between.
17.5.
17.5, quick, 21.
Hey, like, darn.
He has to think about it.
Easy peasy.
All you gotta do is just calculate.
Easy lemon squeezy. All right, now, but what if I asked you, all right, that's fine. Using this graph, then tell me if this is time and this is meters. So this is a displacement or position. And this is time in seconds. Okay, first of all, several of you lost points because you didn't put units down. You didn't label your axis. If you didn't label your axis, nobody knows what it is. Okay? Yeah, you might, but somebody that's going to read it like the grader won't, which means it's a 0. All right, so here's the reason why we don't number it like this. Okay, so tell me, at time equals 9 seconds, where's it located? Oh, therein lies the problem. It's like, first of all, you got to figure 7, 8, 9, somewhere in here? Maybe? Maybe. And then you got to go up, and then you got to go over, so maybe 4-ish? Okay, here's the problem. Is you want to make that decision of where 9 is simple, so that anybody can look at it really quickly and see. Now, I don't think any of you did any crazy numbering like this, but just don't do it. Now, occasionally in math class, it's convenient to put a bit of crazy numbering down. And sometimes in physics or engineering, it's convenient to put a crazy number down. Like, for instance, in math class, the crazy number that you will use a lot would be things like,
Pi over 2.
yeah, pi. And this would be pi over 2, and so forth. But that makes sense because it's a portion of a circle, right?
Are we weak?
All right. Now, for us, in the numbers I gave you, that would make no sense whatsoever. Okay? All right. The main thing, the reason why you all got points off, is because I wanted to see what your graphing skill was. And here's what I saw. All right? I saw things like this. And then students did this. Okay. Yeah, very nice. That's a lovely connect the dots, which is really great when you're in kindergarten or elementary school.
I see Thomas Jefferson.
All right? Here's the problem with this, is every time that we graph, our data, this is not math class, okay? Math class, all your numbers are exact and perfect and pretty. In this class, your numbers are not that way. Your numbers come from an experiment of some kind, or they represent something that, at least in theory, is something that's real, okay? And those numbers have to be measured somewhere along the line, all right? So the deal is that these things have some experimental error in them. And when that occurs, you cannot assume them to be exact. And if they're not exact, you shouldn't draw your line exactly to them. What we want to do instead is represent them with the best representation of the data. Okay, let me show you why this can't be right. So like for instance, maybe say this is a person running. All right? So they're running. So if they're running, that tells you how many meters they go in the first few seconds, right? So they're going a certain speed. What happens to their speed? Slows down, and then speeds up, and then speeds up, and then slows down. Okay, now, if this was a real thing, the person probably did not do that. What probably happened? Well, the people that were timing it, the data collectors, have a little bit of error each time when they collect the data, right? So the person probably didn't speed up, slow down, speed up, and then slow down again. Okay? I used to do this lab out in the hallway where we'd roll a bowling ball down the hallway, and we would graph the data, and it was amazing. Because the students, I'd have them graph it, or first of all, I'd have them take the data with their watch. Okay? What's the inherent problem of timing things with your watch? What?
Absolutely nothing. You just got this stopwatch part.
Now, if you have a stopwatch, that's awesome. But what ended up happening is some people didn't have a stopwatch. Some people did. And so some people had a device that had a lot of precision, and others had a precision of 1 second at a time, right? And so we get a lot of crazy data, all right? Even if you have a stopwatch that has, or a watch that has a stopwatch on it, you still have issues with precision, or with error, because you have timing, like when should I start and when should I stop, right? So there's still issues, even if you have a very precise measuring device, if it's not used properly. So what we end up would be like data like this: data point, data point, data point, data point, data point, data point, stuff like this. All right?
So it went backwards sometimes?
Yes. And students would graph this data, and they'd do this. Well, we know we started at rest, and then they would do this.
That's not.
Okay, obviously this can't be correct because this is telling me that the person went forward, or the bowling ball went forward and then went backwards, and then turned around, right?
They're
Okay.
playing soccer.
Yeah. And we visually know that the bowling ball is just going down the hallway. So how do we correct this mistake?
Best fit term.
Yeah. Unless you know that one of these data points is absolutely wrong, we have to, and we can throw it away. Now occasionally, a student when they're timing that would say, well, I forgot to stop my stopwatch. And so you had a reason to take their data point and throw it away. But if you don't have that, guys, if you don't have that, then you must keep all the data and assume that all of them are wrong in some way or another. They're all wrong. So how can I take a bunch of wrong data and make it into good data? You draw a best fit line. What a best fit line does, there's actually a mathematical equation called a least squares fit. And what it does is it gives you the absolute best average of the data, mathematically. Okay? Now, we're not going to use that in this class, but when you draw a best fit line, what should you do?
Start best near as many points as possible.
Okay, do we start at the first one and end at the last one? Not necessarily. And you need to be careful about that because they will trick you on the AP test and they'll do things like this. They'll make another data point out here. And if you take the first one, the last one, and connect them,
It's wrong.
yeah, it's obviously wrong because look what happens. You have a whole bunch of data up top above it, right? And not very much below it. What you should do is try to put it through the best average of the data. Now, that means that you may not go through any of the data points. And that's okay, because all the data points have error, right?
Oui.
And so you just draw your best fit line. Now, that also is true for if the data is curved. So, the other two graphs I had you draw, one of them was like this, and the other one was like this. And some of you still, let's see, there was like, some of you did this. You did that, and then you did this, and then you did this. Okay?
No, mine wasn't. It was smooth. You just hang.
And remember, we draw a best fit curve. Now, the curve obviously will be harder for you to draw, correct? So there will be a lot more leeway because you don't have drafting equipment with you. And really, for curves nowadays, we don't draw those by hand most of the time. In fact, even these we don't draw by hand most of the time. But guess what? On the AP exam, they'll expect you to graph this by hand. So you have to have practice at it. All right? I gave this to you on purpose without giving you specific instructions because if I gave you all the instructions up front, you would ignore them and you'd do it however you wanted to and you wouldn't remember it. So it's better that you do it, make the mistake, and then, yeah, and your grades suffer, exactly. And now, you'll remember. All right? So there's our best fit line. Here's our best fit curve. All right? That's how you do it. One last thing about this. If we're trying to figure out the slope of this line, never, ever, 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 under any circumstance, use any of these purple data points. Yes, you'll be issued purple crayons.
I've been seeing so long.
Purple!
Keep it purple.
Oh, that was late.
All right, shh. Listen. Okay, here's the reason. Or somebody tell me why. Why do I not want to use the purple data points?
Because they're all wrong.
Because they're all wrong, for one, and they'll give you the wrong slope. If I use these two, I will
Another
get...
line. Oh.
Because there's the slope you get for that set. Here's the slope you get for this set. There's the slope you get for that set. They're all wrong.
And I can't
Yeah.
put second and fifth points. And then it makes it right.
Yeah, you wouldn't even get a slope for this one because it's like really messed
You
up.
get the slope, it would be going from left to right, and then the other line would be going from
It'd be
there.
negative.
So here's the deal, everybody. There is one case I lied. Never, 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 ever use any of the purple data points except,
Oh my gosh.
Closest to the line.
no, not
They're
that they're
on it?
close to the line, if they're on the line. Now, I would recommend, just because, well, on the AP test, when you're doing these problems, okay, what they're going to look for when you graph this data is, number one, can they see your data points? So make sure they're visible. For those of you that draw the invisible data points, those little bitty things, okay, make them nice and big so people can see them, or circle them. All right? Those are, by the way, there's a technical name for these things. Do you know what they're called?
Sorry.
No, they're called point protectors.
Hey, that's a
Yes. All right. So either make your data points big enough for people to see, anyone can see them, even an old physics person grading it, or circle them or box them or something with a point protector. Next thing, you draw your best fit line, and the only time that you can use any of these data points, guys, the only time you can use any of these data points is if your data point is actually on the line. So I could use this data point here, but I got no others. All right? So when you figure out your slope, what I recommend is to find a point on here that matches the grid nice and easy, and another one down here, and then, show which rise over run you're using. Just to let the grader know that you know what you're doing. Okay, we'll talk more about that later. All right, so graphing. Label your axis, make the numbering easy, make them big enough to see. A few of you made them kind of small, so they were hard to read. They were hard to, it would be hard to interpolate, okay, in between the data points. And then last thing is best fit line, and when you calculate the slope, use the line itself, all right? All right, so there we go. Okay, last time we talked about several things. We talked about linear expansion, and remember in linear expansion, the equation L equals, what is it? Okay, I made a mistake. What did I miss?
Delta F.
Yeah, it's the change in length equals alpha, which is the linear coefficient of expansion, which will have to be given to you, or that's what you'll be calculating. This is the original length. This is the change in temperature. In Celsius or Kelvin, it doesn't matter. Now, everybody, I would like for you to write in your notes, just to remind yourself, it doesn't necessarily have to be length. It's just a change in any linear dimension. All right? So we talked about this last time, about if you had an object with a hole in it, that if you heat this up, the object gets bigger. So it could be this length or the width. It could be this length or the height. And it could be this length, which is the diameter. It doesn't matter. Okay, as long as it is a linear dimension, any one of those things will all scale up or scale down at the exact same rate. Okay? So it doesn't matter. So like if we take you and put you in a sauna, you'll get taller and you'll get wider and your circumference will get bigger. Your head will get larger. Right?
Wait. So, we'll get taller and wider. So
Get bigger around.
Will we stretch out?
Will you stretch? No, because you'll get proportionally bigger in all
Oh,
dimensions.
proportionally. So we wouldn't.
It's just like if you put you on a copy machine and hit enlarge.
Okay.
Or we put you in the Arctic, shrink. Then that part, that's a good question. What if, like, if you put your arm in the oven? Yeah, so you'd have baby arm and gorilla arm. Now, will you be able to notice the difference? Not without setting your arm on fire, because remember, this coefficient of linear expansion is this tiny, right? So you only see a sizable change in length if, number one, you start off with a large object already, right? So like if you take a small object and increase it 5%, that's not a big change. But if you take like a building and increase it 5%, well, that could be like 2 meters bigger, right?
Yeah.
And if you have a large temperature change. So in most cases, you don't notice that you change size.
Oh,
Okay.
that's why you said the little line thing.
Now, you'll notice it like we're wearing rings and things like that. They'll get tighter in the summertime and they'll get looser in the wintertime.
That ring in the had to get really hard to get.
Yes. Yeah, the ring and the problem, to heat it up to get it off your finger,
Wow, that was.
yeah, that's not good for you, right? It's like, well, how much was it, 1,000?
No, it was like over 300.
Over 300 degrees?
Yeah,
Yeah, not good.
305 degrees.
Yeah, that would hurt.
Mine was
Celsius.
Just answer my question.
Yeah, 300 something Celsius is beyond boiling.
That's triple boiling.
Mine was 1,999 something. And then
Yeah. Yeah, your finger, you might as well just cut your finger off. All right, so we're through with linear expansion. All right, we began our discussion of the ways that you can transfer heat. And remember we have conduction, convection, and radiation. Okay, 1, 2, 3. Our conduction equation was H, which is the heat transfer rate. So it's in units of joules per second, which is a watt. Okay? So it's the rate at which heat transfers. Okay, what was it again? All right, Ka delta T over L, where this is the thermal conductivity constant. This is the area of contact between the objects. This is the temperature difference between the objects. And this is the length of path Yeah, of this conductivity surface. So like this is really kind of made for like a piece of insulation, right? So you have, or like a wall or something like that. So this is hot over here, cold over here. This is your length of path from heat flowing from hot to cold. And this is your area of contact right there. All right? And then that's K is a constant that you'll have to look up. All right? Or that has to be given to you. All right? We talked about that. So that's our first one. Convection. Convection is just the idea that in a fluid, remember we said that in a fluid, well, remember we said when things get hotter, the molecules vibrate faster, which makes them get larger. Okay, in a fluid, if the fluid, so we have a bubble of liquid here. Okay? H2O, floating in space. All right? And then we heat it up. When we heat it up, it's going to get larger if you add heat to it. It's going to enlarge. Now, think about what's going to happen on Earth if you do that. So here's the ocean, and you've got a bubble of liquid right here. Well, there's liquid everywhere, right? But I'm looking at just this bubble of liquid. And if I add heat to that spot in the liquid, it will get larger. And if it gets larger, has its mass changed? It's still the same molecules, right? But its volume has increased, so its density, and here's the symbol for density in physics. What is it? In chemistry, it's a big D, right? All right, in physics, it's the Greek letter rho. Greek letter rho means density in physics. Density is mass over volume. The mass has stayed the same. The volume has gone up. Therefore, its density has gone down. And what happens in a fluid if you have something less dense? It goes up, and the more denser is pulled down, right? So what happens is this moves up. So convection occurs in a fluid because when something gets warmer, it expands. And when it expands, it becomes less dense. When it becomes less dense, it will rise because of the buoyancy force. Okay? And it will go up. And then the denser stuff goes to the bottom. All right? So you have what are called convection currents. So you can do this if you want, if you get a glass of water and stick it on the stove, and you can actually, if you have something in there to watch, you can watch as the stove makes this part of the water hot, and then that part will rise up, and you'll start to get convection currents inside. Okay, they'll go up, and as they go up, they'll cool, and as they cool, they fall back down and replace the hotter stuff on the bottom that's rising. Okay? Yeah. There are the way we heat and cool, especially the way we heat rooms like this, are not very efficient. Because remember we said that air, because air has a very low conductivity, then it won't transfer heat very well. And it won't absorb heat very quickly. So when we pump cold air into this room, or in the wintertime, when we pump hot air into this room from the air vents, hot air comes in, we got to wait for those very spaced out air molecules to run into us, right? If we had water the same temperature as the air, we would warm up much faster, right? By the way, in a really cold winter day, you can walk outside, and you can stand outside for a long time, and you'll get cold, but you won't freeze, right? But if you jump into cold water, you will lose your heat to the water much faster because the molecules are denser together and you transfer heat faster to the water. Okay, like for instance, if the water's like 70 degrees, the water's 70 degrees. Yeah, that's ridiculously cold. And if it's in the 60s, you won't be able to stand it for very long. You'll die. What was the Titanic? What was the temperature of the water around the Titanic? I don't remember. It was like 63, 65 degrees, something like that.
What scale are we talking about here?
Oh, yeah. Sorry. I'm talking Fahrenheit.
It's like 60.
That's a good point. Good point. Thank you. We got unit issues, don't we? Yeah, 63 degrees, somewhere around there, Fahrenheit, right? Which, if it was that temperature air, it would be a beautiful day. Beautiful day. All right. So anyway, that's convection. We do not have any equations that we will use for convection because convection is quite complicated to model how this works. All right? So we're going to jump to radiation. So no equation for convection. You just need to understand the concept. All right. Last one is radiation. Radiation has a specific equation for it, and here's the deal. When your molecules vibrate, your molecules are made up of charged particles, and these charged particles moving create an electromagnetic wave. So any charged particle, electrons, protons, that move will radiate electromagnetic waves. Now, since you have temperature of any kind, you're not at absolute zero, right? That means your molecules are moving. That means that your molecules are radiating electromagnetic waves right now. Now, since our temperature is not real great, it's not radiation that is extremely large, nor is it something that we can see. Okay, let's talk about the spectrum, the electromagnetic spectrum. This will come back around later in the class. All right, there is the light we see, which is called visible light.
Oh yeah, the little thing that has like red.
Yeah. Roy G. Biv. Red, orange, yellow, blue. I'm sorry, red, orange, yellow, green, blue, indigo, which they don't talk about anymore, and violet.
Red, orange,
Okay? That's what we see. You might want to write this down. Red is 700 nanometers in length. Red, that's the deepest, darkest red that we can see on average. Everybody's eyes are a little different. And the deepest, darkest violet that we can see is around 400 nanometers. Okay? So that's the spectrum that we can see. So this is the wavelength of the waves that we can see. That's a very tiny piece of the electromagnetic spectrum. Ridiculously tiny. Okay? On either side of that is more light. It's light that we can't see. So when we talk about the electromagnetic spectrum, that is also called light. It's just light we can't see. So this is visible light, and this is light in the more broad sense. Okay, what other kinds of electromagnetic waves are there? Infrared, that goes here. Ultraviolet, that goes here. What else?
Radio wave.
Radio. Gamma. Gamma ray. X-ray. You're missing one. Somebody say it? Microwave. Microwave.
X-ray and what ray?
Okay, now in nature, nature doesn't care what we call them. Okay? These are names that we've made up to describe the different parts of the spectrum. These are called radio waves because we originally used these to broadcast radio signals. You could just as easily call them television waves or cell phone waves, if you prefer. Okay? These are the lowest energy and the longest wavelengths. Okay? Microwaves, they're called microwaves because they're about the size of a micron, roughly. That's how they got the name. All right? A micron is a unit of measure in the English system. English measuring system. Infrared. You know why they're called infrared? Yeah, because it's on this side of red. So that means this is called ultraviolet because it's on that side of violet.
That just sounds so cool. Infrared and ultraviolet.
So you can never miss these, by the way. All right? As long as you know Roy G. Biv, you know where infrared and ultraviolet go. Okay, X-rays. Anybody know why we got X-rays? What
Because they didn't know what to call it, so they just called it X.
Yeah, very good. That's exactly what they did. The dude that discovered these, he didn't know what they were. And so he literally called them the unknown ray. And in math, that's the symbol X, the unknown ray. All right? These are called gamma rays. Anybody know that one?
Still don't know. Radiation?
Yeah, actually it's because of, they discovered gamma rays because of nuclear radiation. They found 3 primary things that came from the nucleus. They called it alpha rays, beta rays, and gamma rays. They discovered that alpha was an alpha particle, a helium nucleus. They discovered beta rays to be an electron. And then the gamma rays were an electromagnetic spectrum, so their gamma ray name stuck. That's why they're called gamma rays, okay? Now, these are the highest energy, smallest wavelength. So I'm going to write this down for you to know later. So, small wavelength, there's our symbol for wavelength, it's a lambda. High frequency and energy. Yeah, that's a lambda. Actually, you'll see me write them like this, but you'll see them in books written like this or like this. All of those are lambdas. Okay? Just different ways to write them. Okay, down on the other end, we have very long wavelengths, and we have very low frequencies and energy. Okay? All right, here's the deal. Guess what? The lower the temperature of an object, the slower the molecules are vibrating. Guess what? The rate at which these vibration of molecules occurs matches up with this frequency. So for us, at our temperature range, we're radiating mostly in this range. If you get something hotter, okay, so go home, turn on the oven, turn on the range, turn it on high, and sit there and watch it. Turn the lights off. Don't touch it. And watch it with the lights off. And as it gets hotter, what happens? It starts to glow. What color does it glow first? A really deep, dark red. And then what? A brighter red. And then if you could get it hotter, what color would it? Orangish red. And then yellowish red. And then by that time, it becomes essentially white because it's emitting all of these things, but mostly in the middle here. So it looks like our sun. If you get it around, I think it's 6,000 degrees, it will look exactly, 6,000 degrees. So get your oven up to 6,000 degrees, and it will look exactly like the sun. Because I think the surface temperature of the sun is around 6,000, if I remember correctly. Okay?
I'm sure we can do that.
Yeah, no problem.
Cold in the winter.
Wait, what, has that?
Yeah.
Can you reach that temperature? Like,
Not with your oven. Your oven will get up to around 500 or so degrees.
no, the oven. I know that much.
But can you get this? Yeah, sure.
Yeah, it's
easy.
not like everything spontaneously combusted.
Get a lot of Bunsen burners.
No, I don't think.
And then stick them together, like aim them at the same small little area.
So wait a minute. Wait. Does that mean that if we get you to 6,000 degrees, you will glow like the sun?
Yes.
The answer is yes.
The answer is no. I'll be black.
Before that, you
Now, will you be able to tell anybody about it? No, because you'll be dead.
Wait, why would I turn black?
You won't turn black. You'll turn like this. You'll be the sun.
Burn up first.
But then after we cool you off, you'll be burnt to a cinder, and then you'll be black.
Oh, nice and crispy.
Actually, well, never mind. We'll leave that a go. What if you get even hotter? Well, then it goes over towards this way, and it becomes a bluish white,
Like blue stars.
like blue stars. So blue stars are hotter than our relatively cool yellow star, yellowish white star. And if you look up in the sky and look at, in the next few months, you'll start to be able to see Orion come by. Orion's easy to spot. It's the 3 stars in a row, Orion's belt. All right, if you look at Orion's belt and then look up, when you see Orion's belt, look up and to the left from Orion's belt, you'll see a great, well, it won't be great big from us, but you'll see a reddish star. That's a huge star called Betelgeuse.
Hey.
That's the name. And it's a huge red giant. It has a very cool surface, and so it's reddish. Okay? All right. When you get up to really, really high energies, like near black holes, where things are moving really quickly as they fall in, and the temperatures are really hot, they'll emit X-rays.
So, they look like bones and stuff?
Yeah, so if you stood next to a black hole, then we can stick a piece of film behind you and it would produce an X-ray. That's correct. Yes.
Hey, I think you just my arm.
I'm not kidding you.
Awesome.
Hey, by the way, back when X-rays were discovered, one of the cool things that they did, because they were really neat, that you could immediately take a picture of somebody's bones. All right? Because X-rays have enough energy to penetrate your soft skin, but not through your bones very well. All right? So what you're seeing is a shadow picture of your bones. All right? Now, what they used to do before they realized that X-rays were not really that great for you is you used to be able to go to a shoe store and they'd have an X-ray source and sitting in a box, and you'd stick your foot next to that box, and on the other side of that would be a screen, a scintillation screen, that when the X-rays hit it, it made it glow, and when you stuck your foot in there, you could see live and in person your bones in your foot. They would have that at shoe stores, some upscale shoe stores, to help.
That's awesome.
It was a way that to get people in to look at their foot and then buy shoes,
And get cancer.
and then later get cancer. That's correct.
Toe cancer, oh no.
Yeah, I've got cancer of the toe. You don't want to lose your toes.
Actually, I kind of
All right. So let's talk about this radiation. The radiation is temperature dependent. So in our equation for radiation, you're going to get a temperature component. And that temperature equation looks like this, or the equation as a whole looks like this. Let me see. Here it is. It is P equals E sigma A T. Actually, it's just on our equation sheet. Is it listed? Can you find this one? See if it's on there.
I thought I saw this too.
Is it the pink sheet?
Is that like a delta A or what is that?
All right, that's a sigma. All right, so here we go. Is it on there? Okay. So you'll need to write this one down.
Is that what it really looks like?
Yeah. All right. E equals emissivity. And I hope I spelled that right. Emissivity. Emissivity tells you how well the object emits radiation. Okay? So this ranges from a 0 to 1. It's going to be a number between 0 and 1. All right? So an object that emits no radiation will have an emissivity of 0. All right? An object that has will emit all of its energy by radiation will have a number of 1. Okay? So they'll just have to tell you what that is. All right? Sigma is a constant. It's, I believe it's called the Stefan Boltzmann's constant, if I remember correctly.
All connected, or is that like,
5.6.
like when you draw your sigma, is it like a slanted 6, or is it like two different sticks that you just?
No, it's like a slanted 6. It's all one movement. Okay? Stefan Boltzmann's constant, I believe it's called. It's 5.67 essentially, times 10 to the negative 8 watts per meter squared, Kelvin to the 4th power. That's its units. And that's just a constant. So it's not a big deal. It's just have to remember the constant or write it down. Okay, what's A? Area, it's a surface area. So like for instance, if we're talking about the sun, then we would be talking about the surface area of the sun, right? If we're talking about you, how much energy you're radiating away, we would be talking about your surface area. Okay? All right, T is obviously temperature, and this has to be in Kelvin. This has to be in meters squared.
Well,
Yes, it's not temperature change.
So which temperature are we looking for? It's initial, final, what temperature is it?
Ah, okay, here's the deal. That is its current temperature. So as an object cools off and its temperature goes down, what happens to the amount of energy it radiates? It goes down as well. Now notice that this is P. P is just like H. So these two are essentially the same thing. That is rate of energy emission or radiation.
so it's not temperature change. So then why
Hang on, I'll get you there. So it's in units of joules per second again, or watts. So once again, it's the rate at which heat, not the rate at which heat, rate at which energy in watts is radiated away from the object. Now, if you look at our question, number 6, it says, a house has a surface temperature of, and it's surrounded by a temperature outside that's different. And in my particular problem, my house has a higher temperature than the surrounding air. Is yours like that as well?
Yes.
Okay. All right, if the surface area of the house is given and the emissivity is 1, find the energy radiated per second. Deal only with heat transfer due to infrared, blah, blah, blah. Okay, so here's the deal. Here's why they give you 2 temperatures. Okay, let's say this is me. Let's say that my temperature is 98.6 degrees Fahrenheit. Okay, I'm just going to use Fahrenheit for right now. Bear with me. Now, is that the surface temperature of my skin?
No.
Now, my surface temperature of my skin will be less than that, right? I'm just going to make up a number. I say about 80 degrees Fahrenheit. Okay? Somewhere in that range. All right, now, if I walk, wait a minute, 80 degrees. So what's my body doing? It's radiating energy away and cooling off as it radiates energy away. So it radiates energy away.
Unless you're in Texas.
Now, wait a minute. Can my body also be transferring energy other ways?
Yes.
Sure. If I'm touching the ground, don't I transfer energy to the ground by conduction?
And then occasionally air molecules come.
Yeah, and also I radiate by convection. Technically, it's kind of conduction. The air touches you, and it by conduction takes heat away from you, right? You've seen that before. You take something that's hot, set it on the countertop, and you watch the steam rising off of it. Okay? All right, but let's just talk about the radiation. But wait, there's more.
There's more.
What if the outside temperature is 105 degrees, like it frequently gets to in Texas?
You're absorbing heat.
Whoa, whoa, whoa. That means the air molecules around me, or everything around me, is doing what? Radiating heat. To where? Me. So, it's radiating to me. Which one wins? The outside wins.
Temperature, so that's more.
Yeah, so if you walk outside on a 105 degree day, you lose. You get hotter, right? If you walk outside on a
60 degrees.
in winter, say it's freezing, say it's 20 degrees outside,
You still lose.
you lose only because you're radiating heat away too fast, maybe, right? But even in the wintertime, doesn't the outside radiate heat to you?
Yes.
What about a winner?
What?
You say I'm a loser.
You, well, just, you must accept your destiny. I'm joking. Really. Really, I'm joking. All right. So wait a minute. So what happens is that you're radiating heat away, and the environment's radiating heat to you. When do you stay the same temperature?
It's the same.
when the outside temperature and your temperature is the same. Then you radiate heat away, and it radiates heat to you at the same rate, and then you don't have a net change. Okay, so in your problem, you have a house. Your house has a temperature. It's hot. The outside is colder. You're radiating heat away at this rate. Power equals E sigma A T to the fourth. But if the air is radiating heat towards you, or the environment, guess what? At E sigma A T to the fourth. Now wait a minute. Aren't we talking about the same object that we're worried about? So the emissivity will be the same? Isn't sigma the same always? Aren't we talking about heat radiating in and out through the same area? The only difference is this temperature, right? Ooh, so can't we just do this? The radiation rate out from the house minus the radiation rate in from the environment will equal the net, correct?
Yes.
So that essentially what that's going to be is just E sigma A T to the fourth, oops, T to the fourth, minus T to the fourth. This is from the house, and this one is from the outside.
Yeah.
Does that make sense? So essentially you solve how much radiation is going away, how much radiation is coming in, and you subtract them. But since emissivity, sigma, and area are the same, you can do it all in one step if you'd like. All right? So the only time that you won't gain heat or lose heat is if you're the exact same temperature as the environment. And that should make sense. If you go outside on a freezing day and just lay down in the snow, you're going to lose heat to the snow until when? Until you're the same temperature as the snow. At which point you're frozen.
Or the snow's the same temperature as you.
Oh! Now, that brings up a good point. So the snow warms up and you cool down, and you'll reach an equilibrium temperature in the middle, right? So hopefully you're big enough and the snow is small enough that the equilibrium temperature is more towards your temperature than the snow, right? Then you live. Yay!
That's like putting on a shoelace, you know, like if you pull on it, and then like one side, it's too long. If you pull on it, it's going to go like that.
That's correct. Very nice.
Wow.
I'm glad you explained that because I had no idea where you were going when you said it's just like a shoelace.
Right.
I like that. That's see, every year I learn something new. I would have never, ever, really, ever. Excellent. Okay, now it's time for us to talk about gas laws and start and finish gas laws all in 35 minutes. All right, now we're going to talk about gas laws. Okay, remind me everything from chemistry you know about gas laws.
Nothing.
All right, we've got pressure, volume, temperature. We got an N. We got an R, right? Okay, pressure, volume, temperature. Uh-oh. Yes. We're delving into the strange, strange world of chemistry, right? Yay! Actually, we use moles too, but it's okay. Moles. And then a constant. This is called the universal gas constant. For universal gas constant. It's called, yeah, universal gas constant. The R. Well, U is already used for potential energy and stuff. Actually, you know what? The constants a lot of times are derived One, because of the native language of whoever came up with the idea. It might mean something in that native language. Or sometimes it's somewhat arbitrarily assigned because the letter they want to use is already primarily used for something else. And sometimes it's just kind of random that way. I don't know where R comes from. I mean, obviously these kind of make sense. N for moles and number, I guess. All right, everybody. What's our unit of pressure from chemistry?
ATMs, toys.
Yeah, okay. Lots and lots of talking because lots of different pressure measures, right? Okay. In chemistry, they're very pragmatic because chemistry derived itself from a very practical, experiment-oriented science. Okay? And in an experiment, you don't want to use atmospheres if that unit's too big. So you'd use something else, like torr or something else, right? But sometimes torr is not useful. So they use pascals. All right. In physics, on the other hand, physics comes about things from a different standpoint. Physicists, they're purists. They don't care about the units so much. They care more about the concepts. And so what happens is, in physics, for better or for worse, they pick a standard unit. All right? Everything in physics is derived from a set of standard units. They are, for mass, it's kilograms. For time, it's seconds. For displacement or distance,
Meters.
it's meters. For number of stuff, it's mole. Okay? Number of stuff. For charge, it's coulomb. But now in our modern age, coulomb is much harder to measure than current. So they've redefined this in our modern age. We use amps instead. Because amps are so much easier to measure. So coulombs are actually a derived unit from amps now, which is kind of crazy. But anyway, coulombs are amps. 1, 2, 3, 4, 5.
Wait,
I'm missing a couple.
I thought amperes were
1 coulomb per second.
That's correct. So now a charge is really an amp second. Okay, at this level of the game, why don't we just smile and say coulombs? Okay, but for technical reasons, they've redefined the standard unit to be amps because they can measure amps to a much more precise degree. What am I missing? I'm missing intensity, light intensity.
Lumen. Or lux.
He's trying.
Light intensity is candela.
Yeah.
Or light, shoot, I don't remember. I have to look it up because there's light flux, there's light intensity. I think but the one that we do for light is candelas. And there's one more, there's 7. 1, 2, 3, 4, 5, 6.
Light intensity of...
Not force. Oh, temperature. Duh. Kelvin, thank you. Our last one is temperature. Every other unit in physics is derived from these, 7. So that means, like for instance, force is a Newton, but that's a kilogram meter per second squared. All right? Now, that means pressure, which is, what's our equation for pressure? What is pressure?
IV.
No. What is the basics of what is a pressure?
It's how much
Force per area.
Thank you. It is a force per unit area. So wait a minute. What's our unit for force? A Newton. What's our unit for area? It's got to be distance squared or meters squared. A Newton per meter squared. So if you want to be really technical about it, it's a Newton per meter squared, force over area. So Newton per meter squared, so we have a meter squared down here. So technically it's a kilogram over meters second squared. Oh, that's hard to understand. So we'll stick with a Newton per meter squared. They give Newton per meter squared a name, and it is. It is, I should put units here. It's a Pascal. Or just PA. So our unit here. Our pressure is in units of pascals.
Not kilopascals, just pascals.
Just pascals. Yeah, just pascals. So, bummer. The problem is that means that whenever we use atmospheres or torr or something else, we got to change it all to pascals in physics. It's a unit issue. All right? So everybody, 1 atmosphere, just write this down. When you're doing e-homework, you will use 101.325 pascals. When you use e-homework, you'll use that because in e-homework, if you're off by 1%, it counts it wrong automatically, right? Even if you're in the ballpark, it's off by 1%. Because on the AP exam, they use the approximate value of 100,000. Now they use that because it makes the math simpler when you're doing multiple choice. But the problem is you can't use this on e-homework because you see that and that? That's 1% different, right? A little over 1% difference. So you'll get your e-homework wrong if you use this. So on the AP test you use this, e-homework you use this. Okay? All right. What's that?
Would they count it wrong on the AP if you use 101?
No, that's correct. If you want to use 101.325 on the AP exam, you are welcome to do so, but you don't have to. Okay? All right, volume. Okay, wait a minute. Since our standard unit is meters, so what's our volume? Meters cubed, which is a ridiculously large volume in chemistry. In chemistry, did you ever use meters cubed? They use liters and cubic centimeters and different things, right? Okay, like for instance, this big cabinet over here. That's about a meter deep, a little less than a meter deep, a little more than a meter wide. So it has an area on the top and the bottom of about a meter, and it's about 2 meters tall. So this is about 2 cubic meters. All right?
I don't think anybody would never measure something like that.
Yeah. So like,
Fitting up to be-
yeah, and so like for instance, like in chemistry, when you're making measurements in milliliters, that would be like 0.00000 something meters cubed, right? So it's kind of a cruddy unit from that standpoint. It's very bad for measuring things small, but we're in physics. We stick with our unit, and all we do is we just change the power. So like if you're measuring, like for instance, 1 liter. Is it capital L or small l in chemistry? Capital. 1 liter. A liter is actually a decimeter cubed, right?
Yeah.
So that's actually 1 decimeter cubed. That's a decimeter is 1/10. So decimeters to meter, 1 meter equals 10 decimeters, right? But I have to change that, I have to cube it, right? So if I divide that by 10 3 times, 1 liter equals how many cubic meters? 0.001 meter cubed. Okay? Or we would write it 1 e to the negative 3 meters cubed. All right? That's how we'd handle it. All right, temperature, Kelvin, that shouldn't be a problem. No Celsius, by the way, or we're doomed. All right? Yeah, we'll all die. Mole is mole. And universal gas constant. Okay, in chemistry you had several universal gas constants depending on
What unit you use?
what units you used, right? Now since we use only one set of units, we'll only have one universal gas constant. It's on your equation sheet, it's on your constant sheet. It is numerically 8.pi. It's an easy way to remember it. 8.314 pi, right? So you'll always remember 8.pi or 8.314, and that would be in joules per mole Kelvin, if I remember correctly. All right, there you go. I'll just write mole over here again because it's mole. All right, a mole is measured in moles. All right, now, okay, you remember all that gas law stuff you studied in chemistry? You studied Charles' law, you studied Boyle's law, Gay-Lussac's law, yeah, all those different ones? We don't care about any of those. What's the only one we care about? We care about
Ideal gas?
ye old universal gas law. PV equals nRT. And the reason why we only care about this one is because
It has everything built in.
it has everything built into it. All right? Everything's built into this one law. It's the universal gas law. Okay, it's important to note that this universal gas law was come about experimentally through things like experiments by Boyle and by Charles, and these different people came up with different components of the law. And then it was finally combined into one big overarching equation.
Hence the universe.
Hence the universal gas law.
The universe.
Universe. All right, this equation, when you solve problems with this equation, you have essentially two types of problems. You either have a single state problem or a change in state problem. Okay? Single state or change in state. All right? So like for instance, if I told you to measure the volume of this room with meter sticks, which you could do, and I told you to measure the temperature in this room, which you could do, and I told you to measure the pressure in this room, which you could do, or we could assume it to be 1 atmosphere. It would be approximately 1 atmosphere, right? It varies a bit from day to day. Then you could calculate the number of moles in this room. That would be a single state question. You're only asking about what is it like right now at this point in time with nothing changing. All right? Then I could ask, okay, what if we shut the door so none of the moles of gas escape? We seal up the door and everything with duct tape. And then we set a Bunsen burner in the middle of the room and let it burn for 3 hours. Okay? The temperature is going to change. Will the volume of the room change? No. Will the number of moles change? Not if we seal it off, right? So what else will change then? Pressure will change. Okay, that's a change in state problem, where you're going from one state, one set of conditions, to a new set of conditions. So this is a single set of conditions, or you're changing the conditions. Okay? All right. This is pretty straightforward. You have to be given 3 of the 4, and you calculate the 4th. All right? In this particular problem, you do not have to be given very much information. Like the problem I just gave, where I said we have this room, and we add heat to the room. All right? The important thing in a problem like this, PV equals nRT, it's important for us to realize what things stay constant and what things are changing. Okay? First you have to identify, do I have a single condition or am I changing conditions? In the problem where we have our room and we're adding heat, we have a change in conditions, right? All right, so what's changing? Well, this is staying the same.
Fancy.
This is staying the same. Volume's staying the same. And so what you do then is you rearrange your equation. All of these are staying the same, which means they're a constant. So wait a minute. If these are changing and these are staying a constant,
The P over T has to be constant.
yeah, that means P over T has to be constant. Which means that pressure 1 over temperature 1 must equal pressure 2 over temperature 2. See how that occurs? And which one is this? Which law is this from chemistry? This Charles?
Who cares?
Yeah. I think that's Charles' law. I don't remember.
Someone drives his TV because I think it's Charles. No, Charles off his TV.
It's
No, no.
It's Boyle's?
Boyle drives his Yeah.
Which was the PV constant? Pressure? That's Boyle, isn't it? I think this is, with this one constant, that's Boyle.
We didn't care.
Yeah, all right. Yeah, the whole point is we just created one of them, right? And we don't care which one it is. Right? Okay, what if we had one like this? What if we had a problem like this where we had a cylinder that has a piston inside and the piston can move up and down with no friction? Because we have our imaginary piston, frictionless piston of science. Okay?
Yeah, I know.
Yeah, shh. Don't mention that.
It has weight.
Actually, yeah.
Still.
The question is that it says, well, wait a minute. If it's a frictionless piston of science, then if we put a gas inside here, won't the pressure inside here push the piston
Depends on the weight
out
of
the
the
top? And the answer to that is well, you got two things going on.
It's going down.
Number one, the piston itself has mass, or there will be a mass placed on top of our massless piston. Okay? Yeah, our massless piston of science. Don't forget. And then also, even if there was no mass on there, it wouldn't fly off there unless you were in space. Because what else is pushing down on top? The air atmosphere, right? So the atmosphere pressure on top, there's at least an atmosphere on top, right? So let's say we do this, and let's say this time we get a blowtorch. I can't draw a blowtorch, so I'll draw a candle. All right, we'll put a candle underneath. Blowtorch. Hey, it looks like a blowtorch.
And just extend it. Just extend the bottom. Just make like a little rectangle. At the bottom.
A rectangle at the bottom?
Larger rectangle.
Yeah, no, large rectangle.
That's in the cut when you know
Large rectangle.
And there's blowtorch wax dripping down. Okay, so we have our candle, blowtorch, sorry. And we're holding our blowtorch. All right, now, in this particular problem, from no blowtorch to blowtorch, what stays the same and what changes this time?
Temperature.
Well, it melts
Okay,
up
we have
on
a
the
change in
bottom,
temperature.
so
What else?
volume change.
Do we have a change in pressure? If the piston is free to move.
No, it's a change in volume.
So what happens is when you add heat to this, the temperature goes up and the volume's going to go up. So we have a change in volume, but the pressure, the number of moles, and obviously the universal gas constant all stay the same. Right? Because it has a constant amount of force on the top over a constant area, so you have a constant pressure, right? So in this particular one, I'd like for you to write, what will our equation look like? This time, over here, we had P over T equals a constant, or P1 over T1 equals P2 over T2. What will it look like here? What over here equals what over here?
NR over T. V over T is NR over T.
Okay, let me walk you through it. PV equals nRT.
NR over T.
Say it again.
V over T equals R over P.
Okay, V over T equals NR over P. Now you could also flip the whole thing over and have T over V equals P over NR. It's the same thing. It won't matter, right? Most people will write it this way, but you can flip it over. It doesn't matter. And so, since these are all constants, these right here, we can move all those to one side and move all our variables to the other side. So now what do? That means that this is a constant. So we got V1 over T1 will equal V2 over T2. Does that make sense? All right. And that's how we construct every one of those. It's always the same way. Find out what things are staying constant, what things are changing, and then construct the equation you'll use. Whether it be Boyle's law, Charles' law, whoever's. Or Gay-Lussac's law.
And that's the one who did the best equation.
Oh, is that one?
Yeah, because he's gay. But that's how I figured it.
All right. All right, here's the next thing we need to talk about, and the last thing, really, we need to talk about in terms of gas laws. And I haven't explained why we're discussing gases right now yet, but it turns out that gases are really important for us for thermodynamics, okay? And we'll discuss that tomorrow, Monday. All right. Now, everything about the universal gas law was discovered by experimentation. All right? There is another way to look at this. And the other way to peel this banana is to look at it theoretically. All right? And so what they did is they tried to figure out how a gas behaves strictly from theory and laws of physics. All right? So here's what they did. They built what they called an ideal gas model. All right? An ideal gas model, and they created on paper what they called an ideal gas. All right? So here are the assumptions of an ideal gas. Okay, assumption number 1. All right, you ready? The gas consists of an enormous number of identical molecules. Okay? So just lots and lots and lots of them. So many that you can't count. So the gas consists of an enormous number of identical molecules. Okay, identical, molecules or atoms, doesn't matter really. The gas consists of an enormous number of identical molecules. Okay, there's a couple of reasons for this. Identical because it simplifies the math. They're all the same. Identical, I just said identical. Enormous number means that they will allow themselves to use statistical analysis. Okay, because if you only have a few molecules you're keeping track of, you can't use statistics, right?
Because it changes the...
Right, because when one changes, it changes the overall average. But in an enormous number, you can use statistical analysis. All right, next thing, assumption number 2. The molecules are very far apart compared to their size. This is also known as the mostly empty space assumption.
So very far apart.
Yeah, the molecules are very far apart compared to their size. So like for instance, if you were a gas molecule, then we would be all bunched way too close. Okay? If you were all gas molecules, we'd have to spread you out all over the building for you to approximate a gas.
Maybe even further.
Maybe even further.
I won't consider downtown.
Okay? Yeah, send one of you downtown, one of you to Oak Cliff, one of you to Garland, send some of you to Arlington. Okay? All right. You're going to go to Europe? That's a long way, man. You're a vacuumist. You're a very low-pressure gas molecule, aren't you?
You live a little pressure.
All right. And the lower the pressure, the more they're spread out. Okay, so mostly empty space. All right, number 3, and this one's important, very important. The motion of the molecules is totally random. Now, we've talked about this already, but there's no preferred direction or speed to the gas. So, the motion is totally random. That means, by the way, that the average velocity of the gas would be considered to be 0, because some are moving this way, some are moving this way, and on average, it averages out to nothing, right? The gas stays in place and doesn't migrate. So, totally random motion. Assumption number 4. The molecules behave as hard spheres. This is also known as the pool ball assumption. They assume that the molecules behave like pool balls. Now, pool balls only interact with each other when they collide. Very nice. When they collide. All right, so that means that molecules that pass by each other will not influence each other at all. So no gravitational effects. The only effect they have is when they collide and hit. All right? This also includes the idea that...
So was this 5?
No, we're still in number 4. So the only force that they interact with each other is when they collide, and the collisions will be perfectly elastic. Okay? Now, does anybody... if you have an elastic collision, do you remember what that means?
They bounce right off of each other.
Yeah, all energy is conserved. None of the kinetic energy is converted into like sound or heat or anything like that. Okay? Like for instance, if you ran down the hallway and weren't watching where you're going and you collided with the wall,
You bounce straight back.
yeah, if it was an elastic collision, you would bounce straight back with the same speed that you hit the wall. Yeah, so like if you took a basketball and dropped it and it hit the ground, if it was an elastic collision, it would bounce to the same height forever.
Except that gravity would slow it down after.
Actually, not gravity, but air friction.
And air friction.
Yeah.
Gravity would also pull it down though.
Yeah, but as it pulls down, it would hit and rebounds up with the same
I know,
velocity.
but it wouldn't have as much time to do that because of the air friction also.
Yeah, so if there's no air friction, if you do this in space,
So I'm actually.
if you're bouncing a basketball in space, a perfect basketball, yes, then it would bounce forever.
No, because it would never come back.
Stop. All right, last assumption. Last assumption. The molecules obey Newton's laws.
Do what?
The molecules obey Newton's laws. Now this means that you can apply conservation of momentum, conservation of energy, and all these types of laws, and F equals ma, and all those things to the analysis of the gas molecules, okay? Now, by the way, there's a very good reason why we assume that the air molecules have elastic collisions. Okay, think about what would happen. The air is in this room, it's colliding with you, it's colliding with the floor, it's colliding with itself. Think what would happen if it's an inelastic collision. Really? They would hit, and when they would hit, they would lose some kinetic energy and slow down, right?
And so eventually it will stop.
So eventually they would stop, which means that the temperature of the air would drop to
Absolute 0.
absolute zero, and since they would stop moving, gravity would pull them to the floor. So if they're not elastic collisions, what happens? The air becomes ultra cold and lands on the floor. Since we don't see that happen, we must make the assumption that they're elastic collisions, right?
Yeah.
Yeah.
Right.
So if we reach absolute 0, we just fall to the floor and stay there.
Yeah. So you'd be kicking the air around as you walk. But you would have passed out because you can't breathe and you're frozen.
Wait. So if we're at absolute 0, can like we just be at absolute 0? Does like the whole system have to be?
No, I was just talking about the air.
No,
All right. Now, everybody. Here we go. Bottom line. What does it tell us? When they go through all of this, they came up with the derivation, which I'm not going to do. Because I'd have to look it up, because I don't remember how to do it. Ends up, they get this. PV equals 2/3 N K average. Okay, now, P is what? Volume.
2/3.
2/3, which is a number, right? N. N is,
No.
no, it's not little n. This is number of molecules. Okay, K. What's K? It's not Kelvin.
Average.
Average.
It's average what? No, that's not temperature. It's a symbol, not a unit. Ah, it's average kinetic energy.
So they had every single molecule measured instead of just using Avogadro's number and doing moles.
All right, so, hang on. Hang on. So, a couple of things come out of this. First of all, it looks vaguely familiar. The left-hand side looks just like this. And do you see that we have 2/3 number of molecules, which is, number of molecules is related to number of moles by way of Avogadro's number, right? It's just a different way of counting, right?
Yeah.
All right. So these are very similar. So here we go. nRT must equal 2/3 NK average. Right? Because PV equals PV. Now wait, there's more. Hey, table, that's not paying attention. Number of molecules is the same thing as number of moles times Avogadro's number, right? So I can substitute that in. So I get 2/3 number of moles, Avogadro's number, kinetic energy average, nRT over here. So what happens to my N? It goes away. If I solve for K, kinetic energy average then equals what? 3/2. 3/2 what? RT over N, Avogadro's number.
Yeah.
Right? Well, guess what? Since that's a constant over a constant, they can make a new constant up. So it looks like this. K average, kinetic energy average equals 3/2 K sub B T. Okay, don't go yet. Hang on. Okay, 3/2. This is called Boltzmann's constant times temperature. Okay, out of this, the main thing, which we'll finish up next time, is that the kinetic energy of the molecules is directly related to the temperature of the molecules.
The energy is directly
The
related.
energy is directly related to temperature. So the temperature in a gas is a direct measure of the kinetic energy of the gas. All right, we will finish that up next time.
Almost.